water comprises a small fraction of the total amounts of gas in the atmosphere, it plays a crucial role in our day-to-day weather. This is seen most clearly by observing the water cycle in Earth's atmosphere. The water cycle is the cycle of moving and transforming water molecules from liquid to vapor and back again to liquid. We begin with evaporation from oceans and other bodies of water. As this air rises, it condenses to form clouds. The wind in our atmosphere moves these clouds over land, leading to precipitation. As rain and snow accumulate on the ground, they produce water for lakes and streams while producing runoff back to the ocean. And thus the cycle repeats continuously throughout the course of days to months to years. The presence of water vapor in the atmosphere also plays a crucial role in the formation of something as strong as a thunderstorm or in the development of large-scale monsoons. Now, in addition to the transport of water vapor in our atmosphere, in order to produce the towering thunderstorms that we often observe, there must also be a way to transport heat just as efficiently as water vapor throughout the atmosphere. And in this video, we will examine the most important form of heat transport for atmospheric circulations and for atmospheric objects as a whole, and that is known as convection. In this experiment, we're going to demonstrate the science of convection by examining a density-driven circulation. And the idea here is that we're going to set up a circulation within liquid water, and you can do this with any other fluid, by looking at differences in the temperature associated with the fluid on each side. This is our density circulation apparatus that we will be using. As you see here, it's simply two containers here and here. Each container has the ability to hold 1 liter of water or any fluid. And note that there are valves here that controls whether or not a fluid can enter or exit either one. So right now, in terms of the position, when these two are turned as they are here, that means these two containers are separated from one another. When we open them by rotating it to the left, that means we're going to have an exchange of fluid going from this pipe to this pipe on this side. Now, to set up our experiment, we're going to need to use a few things that you see that's in front of you. So the first thing we're going to do is that we're going to need a heat source and a source that is at room temperature. So for this experiment, the heat source that I'm using is what you see right here. This is a hot plate. And this hot plate is going to heat up this water to something above 100 degrees Fahrenheit. And this is just for the purpose of demonstrating the activity. The second thing we will need would be basic food coloring. So food dye that you can get at any store. So in my case, I'm choosing blue to correspond to the cooler object or the cooler fluid. And I'm going to use red to correspond to the warmer fluid. And the basic idea that we're going to do is that we're going to fill the container that you see here on both sides with water that is at a uniform temperature. And then we're going to connect one side to a heat source, and we're going to connect the other side to something at room temperature. So the first thing we're going to do is to fill up the actual density circulation. So I'm going to open these up on both sides. And now I have standard water that I'm going to pour into our model. As you see, when we pour it in, note that there's fluid going in on both sides. And the idea here is that you want to fill this up to 1 liter on both sides so that you can begin to see the circulation pattern develop. About right there. So right now, On both sides, we have 1 liter of water on both sides at this point. Now what we're going to do is that we're going to turn off the actual valves so that these remain separate. And now at this point, I'm going to add red dye to the side that I will connect to my heat source, and then I'm going to add blue dye to the side that's connected to my cooler or room temperature source. So for this experiment, I'm going to choose my left side here to be the warm side that will be connected to the heat source. So to do this, we're just going to take our red dye and we're going to give this about 10 drops of food coloring. And what should happen over time is that the food coloring should begin to go down towards the bottom, and eventually it will begin to mix all the way through. Now the next is I'm going to put my blue dye on the other side, which is going to correspond to the part that I will remain at room temperature. So then the next thing you need is just something that you can use to stir this properly. And so this can be anything that you can choose that is long enough to reach the bottom. So just to demonstrate that point, I'm just going to use a very long ruler to make sure that my dye is fully mixed. So give this a few swirls. And what you're looking for is a situation where the dye is uniformly spread out throughout the water on the left side. I'll take that out and make sure that you do not cross-contaminate your colors. So make sure you wipe off your stirring rod. And then use the other side to mix your blue. And again, mix around until this becomes uniformly distributed throughout. Oh, right there. So at this point, I have my two sides pieced together. And now what I'm going to do is just connect both sides of this to my heat source. I'm going to connect the left side here to the heat source while keeping this side basically at room temperature. So to do this, the first thing I need to do is just to check the temperature of the water I'm going to use for my room temperature. And that's what this is for. This is just filled with water. And then you have a standard thermometer to just check the temperature. And the idea is to wait for about 10 to 15 seconds to see what reading that you will obtain. So for this, I'm seeing that I'm getting a reading that's somewhere around 71 degrees Fahrenheit, which is pretty close to room temperature. Now in contrast, if I put this into my heat source that's been sitting on this hot plate for about 10 minutes, and I measure the temperature, you will see that this will shoot up immediately. And the temperature is almost 120 degrees. So that means we're going to have a very large contrast of temperature for our experiment. So now what we're going to do is just set up the apparatus by taking the hot source off of taking the water off the hot plate, putting it on the table, and that's going to elevate our particular device. So we have now set up our density apparatus, and we have now opened the channels. And as we see here at the very bottom, notice that we now have a flow of blue fluid coming down from the bottom that you see here. Now, as that blue fluid is coming in, that is going to have direct contact with the entire bottom of the heated source. So that means over time, what we should expect to see happen is that as this heated source begins to warm up the cooler water on the bottom, we're going to begin to see a slow rising pattern with our blue fluid here. And you can already begin to see that as you watch the top edge of this particular apparatus here. So notice that on the other side, we have red fluid that is coming from here and it's going out into this section over here. Now, the only way that you can have red fluid going to my right and blue fluid going to my left is if there is a circulation that is developing, that something is causing the actual fluid to move. And for our case, the only difference in the setup for this experiment is going to be the effects of temperature. Now notice that as this begins to rise a little bit, notice that over here, you begin to see it begin to sink down a little bit over here. Now, as you watch the whole system itself begin to evolve, what you should begin to notice, again, is that there's a slow rising of the blue fluid going up. So it initially started down here. It's now rising straight up in a uniform, consistent manner. Now, the question that ought to be raised at this point would be, what do we think will be the end result of the entire process? Do we think that the fluid on top here, the red that you see here, will always be separated from the fluid down here? Or do we think there will be some mixing that should begin to happen? So to see how this process works, it's good just to watch how the fluid evolves just based upon having this heating source right at the bottom. So right now, we've seen that the layer of fluid that started at the very bottom, the blue fluid, has now risen to just over 30 to 40% of the entire bottom. And then notice that right near the top of that particular fluid, you're beginning to see the process of mixing happening. Notice that at the boundary between the blue and the red, notice you begin to see some little thin blue streaks begin to rise upwards and begin to separate from the fluid. On the opposite end, notice we still have a layer of thin red fluid at the very top here. But notice that on the very back here, there's some sinking that's going on as red fluid comes down to this region. Now, the idea is that right now, just as we had before, we now have a well-defined stratified fluid, where in this case, as this gets warmer, it's beginning to push up into the depth of the fluid. So notice that you're beginning to see that the fluid is not quite blue, nor is it not quite red. It is becoming violet. And that is indicative of the fact that mixing is happening between the red fluid here and the blue fluid that's coming in on the other side. Now keep in mind, this is basically what the atmosphere is in a nutshell. Because notice that the warmest part is going to be somewhere near the bottom, and the coolest part is going to be at the top. It takes a substantial amount of energy and work for warm, fluid to rise from the surface and go all the way up to the top right here. Now, a follow-up question can be given. What happens if you begin to give a little bit of mixing with the actual fluid? So let's take our stirring rod and do a small amount of mixing near the top, and let's see what happens. Notice a small amount of mixing at the top has now moved that blue fluid all the way through, and now you've given it a little bit of a nudge at this point. And what did that nudge basically do? That nudge actually enabled the actual flow of energy, the heat that's being transferred from the bottom to the top, to occur more efficiently. And now what you're beginning to see is rising motion on this side here. And you're beginning to see a little bit of sinking going on the other side. And so now the mixing process has enabled fluid transport to become much more efficient than it would have been ordinarily. Now, let's suppose I did the same thing on the other side. Notice not much is happening on the other side, even when I mix. So that must tell me that one of the important aspects that's driving the circulation, it's not just the physical process of mixing the fluid, it is the temperature difference between the bottom section here and the top section here. Now, in terms of a basic understanding of heat flow, there are two types of heat flow that's going on in this system. The first type is due to the fact that the part of the blue liquid coming in at the bottom is in direct contact with the heated portion here. And when there is direct contact between a heated object and the actual fluid itself, that's typically what we call conduction. However, in order for you to get large-scale transport of fluid by heating, that is what we call convection. And that occurs because the warmed part at the bottom is going to become less dense than the surroundings, and so it's going to rise upwards. And therefore, the cooler portions that are near the top are going to want to sink downward. Now, the final point of this whole video is the following. What's going on in this setup that you see here is very, very different than what happens in the ocean. Within the ocean, you also have temperature differences that are there, but in the ocean, what you will often see is that there are very distinct layers of ocean water. You usually would have warm water near the top, and then you have a sharp division between that and the cooler water near the bottom. Notice here, you're not getting anything like that happening whatsoever. You're not getting a separation of fluids, so to speak. You're getting a mixing of fluids. And the reason why is because there's a heating source that is constantly forcing the actual liquid to circulate around in this container. Now, to understand convection better, we need to understand the difference between temperature and heat. So first, when we think about any gas, when we think about the concept of temperature, we're thinking about the average speed or the motion of all of the air molecules that make up that gas. So as shown in this animation here, as the temperature decreases, notice that the speed of the molecules decrease with it. And conversely, as the temperature of the gas increases, note that the molecular motion and the molecular speed increases as well. Now, that ought to be differentiated from the concept of heat, whereas temperature corresponds to the motion of the molecules and therefore it's connected to the energy that the molecules have. Heat corresponds to the transfer or the flow of energy between a system and something else. Now, the most common form of heat transfer occurs when we are examining temperature differences between the object and its environment. So let's suppose, as in this animation, we increase the temperature. What we see happen here, when heat is added to the gas, heat causes energy to flow into that particular gas. And as heat flows into the gas, its temperature goes up and its motion increases. So temperature corresponds to the energy that, say, a gas holds and possesses, whereas heat refers to how energy is transferred from one object to another. Now, often in the atmosphere, the situation is not in a way in which the heat that flows into a gas occurs when the volume of the atmosphere is constant. That hardly ever happens. However, what we do observe in practice is that when heat is added to any gas in the atmosphere, what we observe is that the pressure exerted by the gas tends to remain about the same. And that's because when heat is added to a gas in the atmosphere, the gas will either expand or it will either contract, as you see here in this animation. Notice when heat is added to the gas expands, the container gets larger. And notice that when heat is taken away from the gas basically contracts. That's what naturally happens in the atmosphere. So when heat is added, the gas begins to expand, something like a balloon expanding when heat is added. And conversely, when heat is removed, because there's a cooling process occurring, that's going to cause heat to leave the system, and that's going to cause a gas to shrink in terms of its volume. Earth's mantle, which is very, very hot, to the actual surface of the Earth. Notice that there is a large-scale circulation that is caused by the temperature difference between Earth's core and the surrounding area. This means that convection is observed not only for thunderstorms, but for all sorts of phenomena that involve heat transport by fluids. The basic background idea is the following. Convection depends on the fact that, in general, fluids expand when heated, as we've just saw, and thus the fluid will tend to reduce its density as it is heated. As a result, the warmer, less dense fluid, or the less dense portion of that fluid, will tend to rise upwards through the surrounding cooler fluid, just as you see here in the mantle picture given to your left. Therefore, if heat continues to be supplied, the cooler fluid that flows in to replace the rising warmer fluid will also become heated, and therefore it will rise. Thus, a current, which we call a convection current, becomes established in the fluid with warmer, less dense fluid continually rising from the point in which heat is applied, and then cooler, denser portion of the fluid flowing outward and downwards to replace that warmer fluid, as you see here in this circulation. This means at the foundational level, convection is an energy transport mechanism, and it's going to involve substantial mixing between warmed, heated fluid and cooler fluid that replaces it. So if a heat source is constantly being generated, that means heat will eventually be transferred to the entire fluid, and therefore you will no longer have a hot versus cold section. You will have thorough mixing and therefore a unified single temperature. In our experiment, that is what happens as heat continues to go from the bottom to the top of the chamber. Eventually, the red dye and the blue dye mix together to give you violet throughout the entire scope of the convection tank. The same is going on in thunderstorms. There is substantial heat that is released whenever there is condensation occurring, and therefore heat is being transported from the actual base of the clouds throughout the entire scope of the atmosphere. So therefore you can think of convection as simply a heat transport mechanism. And therefore you should think of thunderstorms, monsoons, and all of these other large-scale atmospheric circulations as being essentially a response to heat transport.